Okay, so my name is Zenodia Charpy. I'm a senior deep learning data scientist working at NVIDIA. Now, my focus is of training and deploying very large language models. Okay, before we dive into this topic, let's briefly take a look at some demonstration of what these very large language models can do. More specifically, all of the below demonstrations that I'm going to show you is powered by NVIDIA Megatron Turing NLP 530 billion parameters. I hope you like it. First up, it's a virtual assistant at Shannon's Cafe. I'm not hearing the audio.
Welcome to Shannon's Cafe. How can I help you?
Can I have a cheeseburger with a side of onion rings, please?
Would you be interested in our popular toppings for cheeseburger like bacon and fried onions?
Yeah, let's do it.
Done. Added cheeseburger with bacon and fried onions. What else?
What protein options do you have?
We have multiple options. I recommend the double protein burger. Would you like that?
Do you have any vegetarian options?
I can get you a black bean patty instead. Would you like that?
Sure.
Okay, I have added double protein burger with black bean patty to your cart. What else?
Do you have any sides?
We have these 3 vegetarian items: French fries, onion rings, and fried pickles. What would you like?
I'll have the French fries instead of the onion rings, please.
Sure. Would you like some garlic on it?
Yes, please.
Okay, I have added French fries with garlic to your cart. What else?
What salads do you offer?
We have market salad, Cobb salad, fruit salad, and side salad. Side salad is popular with our cheeseburger.
I'll do the side salad.
Alright, it is sunny out there. Would you like to add some drinks? I recommend our lemonade.
Sure.
I'll have a cola.
We have 2 options: Diet Cola and regular cola. Which one would you like?
I'll take the latter, please.
Adding regular cola. Anything else?
That's it. Thank you.
Okay, your total bill is $24.46. Your food will be available shortly. Thank you.
Thank you.
Thank you. Bye.
All right. Well, I hope you noticed that large language models can not only keep track of very long sentences, but also being able to understand the semantic and the meanings. For example, like at the very end, you have the Coca-Cola choices referring to expressed as former and latter choice, and then you can see that the language model get it correctly. Next up is Toy Jensen. He's a very smart guy. Let's ask him some very tough questions.
Hi. Hello.
Hello, Toy Jensen.
Hi, please ask me anything.
What are the greatest threats of climate change?
The greatest threats of climate change are the effects on human health, food security, water supplies, and the environment.
How do astronomers look for exoplanets?
Most exoplanets are found via the transit method. That was the case for the TRAPPIST-1 planets.
Tell me more about that method.
The transit method is when a planet passes in front of its star. The amount of light blocked tells astronomers the size of the planet. The duration of the transit tells astronomers the orbital period of the planet.
What roles do proteins play in our cells?
Proteins are the building blocks of the body. They are the basic materials from which all living things are made. They are needed for the structure, function, and regulation of the body's tissues and organs.
How do they work?
Proteins are made up of amino acids. Amino acids are the basic building blocks of proteins. There are 20 different amino acids that link together in different combinations to form different proteins.
All right, so I wish I were as smart as Toy Jensen. Well, joke aside, this very large language model, you can query it in natural language, and you can see that it is almost an expert knowledge base. And then the smoothness and the eloquency of the response is quite impressive. Now let's take a look at two more examples, which is less polished and more direct from the model. I hope you can see the screen here. On the upper screen, we gave few shots examples. So large language models are great with few shot learning. So let's test it out. I gave 2 parallel English to Swedish translation sentences. So on the upper screen, you can see my name is Zenodia, the Swedish translation. I live in Sweden and I love running, and it's Swedish translation. Now I ask the question, what is your name? The response, as you see below in the bottom of the screen, not only did this model translated what is your name to Swedish correctly, but also it tried to answer to the question, what is your name, by responding, hello, my name is Roger, and its correctly translated Swedish counterparts. Now, this is today's last demonstration. We can see that if we ask it to do math, simple addition, you can see on the upper screen. So I gave an example of the question, and I also give the reasoning and the logic behind how I came up with the solution. So 10 plus 20 equal to 30. Therefore, together we have 30 apples. I ask a very similar question. We can see the response in the bottom of the screen. Not only did this model correctly extrapolate the reasoning behind how I came up with the solution, but it also gave the correct solution, which is 5 plus 1 equal to 6. So together we have 6 apples. Now, in these last 2 examples, I'd like to highlight one thing. That is, the way you query the model matters a great deal, actually. Now, I'm going to put a pin on this, and I'm going to pick it up right at the end. So I hope it becomes clear to you that the reason why we want to train very large, deep, huge language models. So the size of the model matters too. We're going to talk about that later. The reason why we want to train these large language models is because once we have trained it, well, we can ask it a variety of downstream tasks with very few labeled data, as we have witnessed above in the demonstrations. Now, the size of the model matters. To get to the performance that we have seen, well, you need to be in the upper right quadrant. And more specifically, again, the one that we have seen above in all of the demonstrations at its very core is using Megatron Turing NLP 530 billion parameters GPT-3 models. So how do we come to have this very large language model in the beginning? How does it born? We need some basic ingredients. First, the data, very large quantity and quality of it. Second, the AI infrastructure that include the hardware and the software. Last but not least, the collaboration. Now, I would like to pause here and make sure that I highlight and emphasize on the partnership between NVIDIA and WARA Media and Language Research Arena, as well as the researchers hosted in AI Sweden and RISE. Without this collaboration and partnership, all of the below that I'm about to say is not happening. So through this partnership, we have already trained a 3.6 billion GPT-3 model using a variety of data set. Now, in order to scale the model sizes to the next target, which is 175 billion GPT-3 models, we will need a lot more data. Now, we reach out to our neighborhood countries, which is Norway and Denmark. Hopefully, we can form this collaboration, and together we train a large 175 billion GPT-3 Nordic multilingual model. Moving up, AI infra. I'm going to talk about hardware first. So in Sweden, we are very lucky. We have a NVIDIA SuperPOD called Berzelius. This NVIDIA SuperPOD Berzelius has 60 nodes. Now you might ask the question, why do I need such a big compute resources in order to train language models? Let's take a look at on the left-hand side of the screen. For training, especially with this row that has 175 billion parameters, because that's our target model size. For a 3 NVIDIA SuperPOD, 60 nodes, that's the same size as Berzelius SuperPOD, it will take 72 days training end-to-end at its full capacity. Now, if we use 1/3 of that compute capacity, it will take 31 weeks. Now, if we actually only use 4 DGX A100 machines, it will take 3 years training exactly the same model end-to-end. Now, I hope that is becoming clear to you that we do need Berzelius, this wonderful SuperPOD here we have in Sweden. Now, having a powerful compute resources is not nearly enough. We need a software framework that's able to utilize the underlying hardware at its full capacity, or as big as it can. That's the NVIDIA provided software. It comes in 2 flavors. On the left-hand side, we have Megatron LM. It is an open source research Git repo. Anybody can have access to it. You can put around it if you have access to a SuperPOD. Now, as we can see, the reason why this framework is important is because that as we scale the model size, here we only seeing 4 examples, but you have more model sizes example possible. As you scale the model size, the performance of the underlying hardware measured by teraflops utilization in percentage does not drop. That's the kind of linear scale. I think you scale the model sizes with the GPUs, number of GPU available to you. This type of framework needs some sort of tuning. You need to tweak the knots of the configuration. Now, Megatron LM comes with, the default PyTorch data parallelism, model parallelism, tensor pipeline parallelism, and optimization of the pipelining. Now, as of May 10th, we have innovated ourselves again. Then now we included the sequence parallelization, activation checkpoint optimization included into the new repo. So if you look at that Git repo, the public one, you will see those changes reflecting exactly those teraflop percentage utilization achieved here. Now, as I said, it is take a bit of a work in order to get it right. That's the reason why we created another framework called Nemo Megatron. It's a enterprise ready for training and inferencing optimized framework. What does it do? It comes with this complementary tool called hyperparameter tuning tool. And as you can see on the right-hand side of the screen, it takes into constraint of, for example, the training constraint or the inferencing constraint, your allowance of the compute resources, for example. That's the constraint they take into consideration. This tool automatically recommended you the best model sizes as well as the best configurations that will ensure performance guaranteed and help convergence. Here's an example of a throughput and latency. This tool will recommend a variety of combinations of that when it comes to deployment of the model. Of course, one should review that what is the best recommendation versus my reality. So this recommendation will be fitted to your scenario. Moving on, now we have talked a lot about the data as well as the AI infrastructure, including the hardware and the software. Now let's talk about the very important aspect of the entirety of what makes this possible. It is the partnership between NVIDIA and WASP, especially WARA Media and Language Research Arena. So I'm gonna show a few highlights of this collaboration. First up is the first best practices scaling and performance exercise conducted on Berzelius SuperPOD, the first multi-node on language models across multi-nodes. Now, on the left-hand side, this is a very complex table. I'm not going to go through all of it. I just want to highlight the fact that using the software, if we look at the first few lines of the gray colored band, using the software with the same model sizes, which is 18 billion, we need to tweak it in order to find the best teraflop in percentage utilization on the left column. So that we can see that not only did this reflected on the underlying compute resources, which is Berzelius, using exactly this framework, Megatron ML, but also we want to ensure that we are not kidding ourselves. We also use profiling tool that is inside on the right-hand side. So we collect the matrices during the job running. So here we select a few GPU from each node, and then we visualize it on inside dashboard. As you can see, the blue bar is almost at the top for each and every GPU. This means that the GPU utilization is maxed out. That's what we want to see. Except for that dent almost at the end, that's checkpointing. So that's the power of utilizing a good software framework that can leverage the underlying hardware to its applicational level maximum. The next highlight is the knowledge transfer session. As said, to use this, tuning this software is not an easy task. So we specifically, under this partnership, created a tailor-made bootcamp to do knowledge transfer. During this bootcamp, we also have a live debugging support complementing this bootcamp with screen sharing and Slack chat. As you can see, it helped the researchers to accelerate and progress on their research via simple debugging sessions. Last highlight is this NeMo Megatron framework. As I previously said, it helps you not only train your model, but also to assist you to carve out a custom road on the left-hand side. We can see this green dotted line. We utilize the existing already trained 3.6 billion GPT-3 model. We test run on this deployment route, make sure it works, so that once we train the 175 billion GPT-3 model, we know there's a way to deploy it with optimal performance and configuration with regard to the deployed model in order to open up a variety of use cases. Now we're almost at the end. I'd like to unpin what I said in the beginning. So, quick recap, in case everyone forget. So what I said is that the way you query the model matters a great deal, actually. In order to get to the optimal response via the optimal way of querying the model, what if we have a way we can automatically tune the way we query the model in order to get optimal response. That would be great, isn't it? Enter p-tuning. So, as we can see, if we can train this tiny neural network called the prompt encoder. This prompt encoder, as you can see on the right-hand side of the screen, in this case is 132 million parameters. This is a trainable parameter. We hold this 3.6 billion GPT-3 models weight freezed, non-trainable. This is the way that we can tune this tiny neural network in order to interact with a big model. That opens up this following possibility, which is if we can deploy and serve this big model, right now it's 3.6 billion, but we're going to train the 175 billion model. Once that's trained, we freeze this model and host it, deployed it in the central organization, open it up as an API call in the middle. So on the client side, anyone who is interested in utilizing this fundamental GPT-3 model can build upon it, bring in your own data with very few label data, and then you can train your tiny neural network, which is the prompt encoder, interacting via the API call. Hopefully, this will ensure that we open this up for innovations and go-to-market ideas. Now, to summarize what I have said thus far, everything we have done here is thanks to the partnership between NVIDIA and WASP, specifically WARA Media and Language Research Arena, as well as the researchers hosted in AI Sweden and RISE. Now, in the bottom, we have already trained a Swedish GPT 3.6 billion model. We want to scale up to get more data, more quality of the data in collaboration with our neighborhood countries. We have already secured the AI infrastructure, including the hardware, which is our wonderful Berzelius, and the software framework. We know how to maneuver over it. We know how to deploy it. Now, the only thing that's left to do is to train that 175 billion GPT-3 Nordic multilingual model and deploy it and serve it for the masses via p-tuning. That concludes today's talk, and I will now take questions.